Welcome students to MJC Learning. My topic name is Thermodynamics and it is fourth lecture of Thermodynamics. Previously we studied about isothermal process. While studying isothermal processes, we saw what was the work done during this process and what is the relationship with the internal energy and heat. So now we will be talking about different processes like isochoric, adiabatic and isobaric process, and their derivation and what is the relationship between work and internal energy and what is the equation of work done in that process. Now thermodynamic processes and their state equation. State equation, here we are going to consider only PV is equal to nRT, where n is the number of moles. Previously I said n is equal to number of molecules per unit volume, which is actually capital N and this is small n, therefore it is known as number of moles. We are going to consider ideal gas undergoing different processes. Here first equation, PV raised to n is equal to constant. If you substitute n is equal to 0, Vn will be nothing but 1. Therefore P is equal to constant. This is a state equation for isobaric process. If n is equal to 1, then PV is equal to constant, which is an isothermal process, which will be a state equation for isothermal process. nRT is again isothermal process where temperature is constant. If n is equal to gamma, what is this gamma? Gamma is adiabatic ratio, which is Cp upon Cv. Cp and Cv we have already studied in thermal expansion in 11th standard. Cp is specific heat, molar specific heat at constant pressure, and Cv is molar specific heat at constant volume. Cp is always greater than Cv. Next is, if n is equal to infinity, volume will be constant, which will be isochoric process. So these are state equations which we will be using in different processes. So first is our isochoric process. Isochoric processes means volume is kept constant. Then the work done will be 0 because gas is not expanding. Heating a gas in a constant volume container or diffusion of gas in a closed chamber are some example of isochoric process. As you can see, isochoric processes, first we will be finding is work done. W is equal to P dot dV. As dV, change in volume will be 0 because volume will be constant, so Vf minus Vi will be 0. So work done will be here 0. First law of thermodynamics, delta Q is equal to delta U plus delta W. As delta W is 0, delta Q will be equal to delta U. We all know that molar specific heat at constant volume Cv is equal to 1 by n Q by delta T. You can refer this equation from thermal expansion. Q is equal to Cv n delta T. We are going to just substitute Q. C is equal to Cv n delta T, where Cv is specific heat at constant volume, that is molar specific heat at constant volume. So first law of thermodynamics will be Q is equal to delta U plus W. Q will be nothing but delta U. Delta U is equal to Cv n delta T. I have just substituted Q value from molar specific heat at constant volume to delta U. So this equation gives that total energy supplied to the system is converted into internal energy. So in isochoric process, delta U is equal to internal energy will be depending upon temperature, change in temperature, and work done will be 0. Next is isobaric process. Isobaric process in which pressure remains constant. Boiling water at constant pressure, normally at atmospheric pressure, is an isobaric process. Delta P will be equal to 0, change in pressure will be equal to 0. So work done will be nothing but P Vf minus Vi. I have already done this equation in previous lecture. Now Vi and Ti are initial volume and initial temperature, and Vf and Tf are final volume and at final temperature. Subtracting 1 from 2, you get P in bracket Vf minus Vi is equal to Nr Tf minus Ti. From previous derivations, You have already know delta U is equal to NCV delta T, where delta T is nothing but final temperature minus initial temperature. By substituting this delta U in first law of thermodynamic equation, you get Q is equal to NCV Tf minus Ti plus P in bracket Vf minus Vi. Now you can also see again same equation here, P in bracket Vf minus Vi is equal to NR Tf minus Ti. If they are both same, they are both equal, then I can substitute value of P Vf minus Vi is equal to NR Tf minus Ti in equation of first law of thermodynamics. So it will become NCV Tf minus Ti plus NR Tf minus Ti. Therefore, Tf minus Ti, taking out both common from these two, we will be getting Q is equal to Tf minus Ti and Cv plus R. You know R is equal to Cp minus Cv. This is again proved in your thermal expansion. Cp is equal to Cv plus R. Therefore, Q is equal to Tf minus Ti and Cp. Now, temperature of the system changes in isobaric processes. Therefore, its internal energy also changes. So, in isobaric processes, work done is nothing but P Vf minus Vi or Nr Tf minus Ti, and its heat will be Tf minus Ti and Cp. Last is our adiabatic process. In adiabatic processes, there is no transfer of heat or no transfer of heat from or to the system. Heat transfer to or from the system is prevented by either perfectly insulated or insulating from the system and its environment, or by carrying out the changes rapidly so that there is no time for any exchange of heat. When the system expands adiabatically, work is positive and internal energy is negative. When a system is compressed adiabatically, W is negative and delta U is positive. I have already told you, if it is compressed, then work done will be negative, and if it expands, work done will be positive. So, in adiabatic processes, there is no transfer of heat from or to the system. Therefore, Q will be 0. First law of thermodynamics will be delta Q plus delta U plus delta W. As delta Q will be equal to 0, therefore delta U is equal to minus delta W. Now we want to find out work done. So W is equal to integration of P dV from Vi to Vf, initial volume to final volume. Now going back to our previous equation, first equation, here PV raised to gamma is equal to constant. This is for adiabatic process. So we are substituting this PV, this is equation for PV raised to gamma is equal to constant, which is represented by C here. PV is equal to C by V raised to gamma. Also, internal energy is given by delta U Cv delta T. This is again followed from the previous derivations. So W is equal to integration from Vi to Vf C V raised to gamma dV. Just substituting P value from adiabatic equation to work done equation. Okay, the same equation is written here. W is equal to integration Vi Vf C Vr V gamma dV. So C is again your constant, so it will come out, and if you do its integration, you will get V raised to minus gamma plus 1 upon 1 minus gamma from Vi to Vf. C 1 by gamma, again gamma is constant, 1 by Vf gamma minus 1 minus 1 by Vi gamma minus 1, where Vf and V are initial and final velocities, final volumes. Now this C is equal to Pi Vi raised to gamma and Pf Vf raised to gamma, already mentioned here. In adiabatic process, Pv raised to gamma, this equation, this equation. So here, so PV raised to gamma is constant, therefore P initial V initial raised to gamma is equal to P final V final raised to gamma is equal to the same constant. By substituting their values in this equation, by multiplying this C into inside, we get PF VF gamma minus PI VI gamma upon VF raised to gamma minus 1 minus VI gamma minus 1. So if we further calculate it, you will get PF VF minus PI VI into 1 upon 1 minus gamma. This is work done formula, one of the work done formula. Now next is this PF VF is equal to nRTF, PI VI is equal to nRTI. This is again the ideal gas equation. So you can substitute PF VF nRTF minus nRTI. So you will get nR is again constant upon 1 minus gamma TF minus TI, or nR 1 minus gamma in bracket TI minus TF. Now this second or equation should be in negative, means minus nR 1 minus gamma into Ti minus Tf. I am going to write this equation again in the next slide. So let us go for this explanation. When the gas expands, work done is positive and Ti is greater than Tf, means initial temperature is greater than final temperature. This means that the gas cools. Similarly, if work done is smaller than 0, that is negative, then Ti is smaller than Tf. This means the gas will warm up. Again, I am telling you that work in adiabatic processes here in the second equation is or equation. Minus should come outside. Okay. This was the last slide. Now next will be cyclic process and different types of heat engine. Now you have understood something about processes. Now these processes will be used in where are their applications are in diesel engine, auto engines, in which you already know that air and petrol vapors are mixed, and these are our system now. When it is ignited, it will expand. This expansion will cause to adiabatic processes, and when piston will move inside, it will compress, heat will be developed there. So this all processes will actually basically give you how engine works. So it's a very basic branch of engineering. So if you want to do some engineering stuff, you need to understand what is thermodynamics. Thank you for this time.